If a magnetar appeared halfway between Earth and the Moon, every credit card magnetic strip on our planet would be wiped clean instantly. Its magnetic field exerts physical force across 100,000 miles of empty space. Credit cards store encrypted banking data using microscopic iron oxide particles aligned in precise directions. Standard magnetic payment readers require only a few hundred Gauss to alter those patterns and erase stored financial information. A magnetar produces over 1 quadrillion Gauss at its solid crust surface. At a distance of 100,000 miles, that magnetic field weakens following an inverse cube power law, yet still arrives at several thousand Gauss. That strength effortlessly scrambles stored binary code on every magnetic media strip across an entire hemisphere. Moving closer toward the dead star exposes physical matter to forces that destroy chemical structures entirely. At a distance of 1,000 miles, the magnetic field deforms atomic structures by pulling spherical electron clouds into thin cylindrical needles. Covalent bonds break down because electrons can no longer form stable shared molecular orbitals. Human tissue would dissolve at that range because organic water molecules lose their fundamental geometric shape. The field's sheer intensity forces biomolecules apart without touching the body, causing total molecular disruption through magnetic power alone. Astrophysicists once believed stellar magnetic fields could never reach such extreme intensities in nature. Standard physics textbooks throughout the 1980s capped maximum neutron star magnetic fields at roughly 1 trillion Gauss, assuming higher fields were unstable. The dense celestial objects responsible for these extreme environments are not giant black holes or colliding galaxies. They are dead stellar cores smaller than the width of Manhattan, known to modern astrophysics as magnetars. On March 5, 1979, Soviet Venera probes and American satellites recorded an unprecedented gamma radiation surge. The blast swept across the solar system, instantly overloading radiation detectors on 9 separate spacecraft in orbit. Triangulation placed the source inside the Large Magellanic Cloud, 55 kiloparsecs away from Earth. In less than a tenth of a second, the mysterious source emitted more energy than our Sun produces in 3,000 years. Astronomers designated the object SGR 0526-66. Unlike standard cosmic gamma-ray bursts that occur once during stellar collapse, this source repeated shorter energy flashes over subsequent months, creating a completely new astronomical classification. Scientists named this newly observed class of high-energy cosmic phenomena soft gamma repeaters. For over a decade, the physical mechanism driving these repeating gamma-ray explosions remained an unsolved puzzle across the theoretical astrophysics community. Mainstream astronomers argued that accreting neutron stars pulling hydrogen gas from companion stars caused the sporadic flashes. However, that accretion model failed to explain why energy output exceeded the theoretical Eddington limit thousands of times. Gas pressure should have blown accretion material away long before such extreme energy levels could accumulate. In 1992, astrophysicists Robert Duncan and Christopher Thompson proposed a radical theoretical model to solve the puzzle. They calculated that a rapidly rotating newborn neutron star could drive an internal convection dynamo. That convective process would amplify internal magnetic fields to over 10 raised to 15 Gauss within 10 seconds of collapse. Their equations showed that a magnetic field that strong would exert immense stress on the star's iron crust. The crust would eventually fracture under tension, releasing giant bursts of magnetic energy as repeating gamma radiation. When a massive star dies in a core collapse supernova, its remnant collapses into a ball 20 kilometers wide. Conservation of angular momentum forces this newborn neutron star to spin hundreds of times every single second. If the collapsing core spins faster than once every 10 milliseconds, violent thermal convection occurs inside. Hot nuclear fluid moving outward combined with rapid rotation amplifies seed magnetic fields exponentially through a turbulent dynamo. Within seconds, this convective dynamo converts heat and rotational energy into intense magnetic flux. The internal field reaches 100 billion Tesla, embedding itself permanently into the solid iron polymer crust of the dead star. For years, mainstream astrophysicists dismissed the Duncan-Thompson magnetar model as pure theoretical speculation. Critics argued that magnetic fields of that magnitude would float upward and escape the star before ever stabilizing inside the dense core. Direct observational proof arrived in May 1998 through observations led by astrophysicist Krissa Kuviliatu. Using data from the Rossi X-ray Timing Explorer, her team measured the spin period of soft gamma repeater SGR 1806-20. The object was spinning down rapidly, losing rotational momentum as its magnetic field dragged through surrounding space. Calculating the magnetic braking rate yielded a surface field strength of 80 trillion Gauss, proving magnetars actually exist. Today, astronomers have confirmed 31 active magnetars within our Milky Way galaxy out of billions of stars. They represent roughly 10% of all neutron stars produced by core collapse supernova explosions throughout galactic history. These dead stars spin far slower than typical young pulsars because magnetic drag decelerates them rapidly. A typical magnetar rotates once every 2 to 12 seconds, converting its stored magnetic energy into high-energy radiation. On December 27, 2004, at 21:36 UTC, a colossal energy wave struck Earth. The blast came from magnetar SGR 1806-20, located 50,000 light-years away in the constellation Sagittarius. In 0.2 of a second, the giant flare released 1.3 times 10 to the 46 ergs of energy. That single event emitted more energy than our Sun produces over 250,000 full years. The gamma-ray wave was so intense that it blinded orbital gamma-ray observatories instantly, including NASA's Swift satellite. Detector instruments saturated completely because they were designed for faint sources located billions of light-years away. Particle detectors on the German-American Wind spacecraft were knocked off scale despite being heavily shielded. Even satellite instruments pointing completely away from Sagittarius recorded secondary gamma rays reflected off the lunar surface back toward Earth. Despite originating 50,000 light-years away across the galaxy, the energy wave directly altered Earth's upper atmosphere. The sudden ionization expanded the upper ionosphere downward, dropping its boundary height from 80 kilometers down to 30 kilometers. Transatlantic very low-frequency radio communications were severely disrupted for hours as the nighttime ionosphere reacted like daytime. Scientific instruments recorded measurable atmospheric disturbances worldwide caused by a dead star on the far side of the galaxy. If that exact giant flare had occurred within 10 light-years of Earth, consequences would have been catastrophic. The blast would have stripped away our planet's ozone layer, driving severe radiation levels and potential mass extinction. Calculating the giant flare's total energy output proved that the magnetar's internal magnetic field exceeded 1 quadrillion Gauss. That event confirmed that magnetars host the most powerful magnetic fields anywhere in the observable universe. The mechanics driving these colossal eruptions stem from magnetic stress building up inside the neutron star. As the internal magnetic field twists, it exerts immense mechanical force against the solid crust, dragging it along. When the iron lattice crust reaches its mechanical yield limit, it snaps open in a massive starquake. This magnetic reconnect ion event accelerates relativistic particles into an expanding fire cloud of gamma rays trapped by magnetic fields. Beyond giant flares, magnetars are now the primary candidate for solving another major cosmic mystery: fast radio bursts. In April 2020, radio telescopes detected an ultra-bright radio spike from magnetar SGR 1935+2154. That detection provided the first direct observational evidence connecting local magnetars to mysterious millisecond radio signals from distant galaxies. It proved that magnetic reconnect ions on magnetars generate coherent radio beams visible across billions of light-years. Magnetars do not maintain these extreme magnetic fields forever. Over roughly 10,000 years, internal magnetic energy gradually decays into thermal heat, leaving behind a cold, quiet, invisible neutron star drifting through interstellar space. Hundreds of thousands of these extinct magnetars currently cross our galaxy completely undetected by optical and radio telescopes. Their extreme magnetic fields have faded, but their superdense cores remain as permanent dark remnants of ancient storms. Every credit card on Earth remains safe today because the nearest known active magnetar sits thousands of light-years away. Yet out in the dark, 31 active magnetic monsters continue to strain their solid iron crusts in silence. Astronomers estimate that thousands of unidentified magnetars drift unseen through the Milky Way's spiral arms. A single sudden crustal fracture on a nearby unmapped remnant could reach our planet long before we ever detect its approach.